Thanks, Andrea, and hi, everybody. So, as you can see on this slide there, and you know that now 40 years ago almost, AFM started or get invented basically to look into the surface topography. But nowadays, it has evolved tremendously so that now we can actually look into the characterization of many properties of samples and materials at the nanoscale, including electrical, mechanical, thermal, electrochemical, and even chemical characterization. And sometimes we can also use the AFM probe for nanofabrication. So today we are going to focus on the nanoelectrical characterization in this webinar, and we are going to go through an overview of the methods that we can actually use for the characterization of materials. Yeah, I think. Now, whenever we talk about electrical, the first thing that intuitively comes to mind is currents. So electricity is current, and basically we can measure the currents at the nanoscale, which tells us about the conductivity of the materials. Here I show an example where you can see on the left image the surface topography of an iron oxide, and on the right image the corresponding current measured simultaneously with topography while the AFM probe is in contact with the surface. So on this image, the contrast represents the value of currents. Brighter contrast means more current, which means higher conductivity of the material at that spot, and darker areas are for low conductivity or zero current. Interestingly, you can see that with AFM, we can measure actually different levels of current, so different levels of conductivity, which in this case is likely related to the thickness of the oxide. So now if we move on this table, we shall look at the type of properties that one can look at the nanoscale, and that's on the first row. So it's conductivity, electric fields or charges, carriers, dielectric properties, piezo and ferroelectric properties. And on the first row of the first column, what we can look at are the different modes available in AFM for the nanoelectrical characterization of these different properties. So we will get back to this table as long as we move on in the presentation today or the webinar. But just that you know, these dots that you see are just to represent basically how much each method is more or less suitable for this type of property to measure. So if you take an example, this KPFM here, for carriers measurements, it's less suitable than, for example, SEM or SMIM. Okay, so we will get back to this table as we move on. And another thing that is important to note, and here I go back to the same example of this iron oxide, it's not only that we can measure images or obtain images showing the variations in terms of contrast for the current, but basically we can also do spectroscopy. And in this case, it's like the current versus voltage curves, so IV curves, locally at each different points of the surface. And this allows us, when we do this spectroscopy, to go further in studying the functionality, the nanoelectrical functionality of the material that we're measuring. So here you see at different points, pointed with these different triangles, we see that the material behaves differently from the point of view of electrical behavior. So yeah, I think this spectroscopy functionality is possible for different methods, but not all methods in nanoelectrical characterization with an AFM. And basically, we go back to this table, you see that conductivity, carriers, dielectrics, and piezoelectric materials could all be characterized spectroscopically as well as per imaging, right? Now, the only thing that is challenging when we do measurements of electrical properties, especially conductivity, for example, is that the needs to be in physical contact with the surface. So the challenge is basically we are involving lateral forces, which cause actually damages to the probe or to the sample and limit the reproducibility of measurements, especially if we are dealing with fragile or soft materials. So maybe this code is now like 14 years old, but very interesting to mention, saying that perhaps one of the most significant practical challenges to use in CAFM, which is conductive AFM, is obtaining a good electrical image without causing significant damage to the sample. So patience and willingness to sacrifice many AFM cantilevers in the name of science are often necessary. So probably this resonates with a lot of people who already tried to do conductive AFM in contact mode. Now, what is the solution for that is actually to switch into the peak force tapping method of measure, which is based on continuous force curve-like operation, where the tip intermittently touches the surface during a certain time. So as you can see on these graphs here, we see the force versus time, which means that at the beginning, the tip is not touching the surface. It's away. It comes close to the surface, touches it for a certain time. So that's the contact time, and then actually moves away from the surface. Now, to measure the electrical property, and more specifically in this example, the conductivity, the current, we need to do that only during the contact time. And as you can see here, these are real-time screenshots of actually the deflection signal, so the force, and the measured current during these force curves. The time is extremely short, which means that you need really very advanced electronics to be able to do that. And that's possible with the methods we'll be showing in the remainder of this webinar. I think. So for that, we finally go to this final representation where we show which methods apply to soft materials, which methods actually can also include spectroscopy, and obviously all methods include imaging, right? So as you can see, most of the methods, or almost all the methods basically, except SCM, they have this green color, which means they are suited for measuring fragile samples. And this actually propels the application of AFM for electrical measurements, because now we can actually look into very, very soft materials, even in biological samples, for example. I think. And from here now, we are going to look into the conductivity and all the methods associated with it. And now I hand it to Peter.
Thanks, Khaled. Always a pleasure to do a joint webinar with you. I'll focus on the first property category, which is conductivity. And as we go through the webinar, we'll also address the other columns with examples and going a little bit into detail on how it works. So conductivity first. Conductivity is probably still the most used electrical method in AFM of all the ones that are listed in the table. Principle is pretty simple. We put the tip in contact with the sample, or continuously, or during like the peak force cycle intermittently. And while doing that, we apply a DC voltage and measure the resulting current. Currents can often be very low, or currents can sometimes vary over a large range. And in function of what we expect in terms of current, we'll be using a specific current amplifier, often going to extreme low currents. And as Khaled pointed out, there's in most of these modes, there's an imaging element. Here we are mapping the conductivity of metal contacts that are contacting devices that are located below these metal contacts. And the different devices are reflected in different conductivity levels, as well as spectroscopy, in this case, IV spectroscopy collected on selected contacts. This is typically done to identify defects or failures in specific devices. The resolution of this mode can be as good as atomic resolution. And that is not the case for all of these electrical modes. There's actually only a very few of these electrical modes, and including the conductive AFM. So here's one example on H2PG. There is a published example with the reference below, where graphene has been irradiated with different laser doses, and the effect on the conductivity at the atomic scale is measured in this publication.